Welcome to our first discussion on writing mathematical proofs. So, in this series of videos, what we're going to do here is going to go through some basic techniques to use when writing mathematical proofs. Okay, so I'm going to talk about mathematical induction, contrapositive proof, contradiction. We have direct proofs, proving equality of sets. Two sets are equal. Proving when you're gonna say that two numbers are equal and the rest. Okay, so the first thing I'm starting with is using mathematical induction. Okay, proving some proposition in mathematics when you are using mathematical induction. All right, so mathematical induction actually comes in two forms. You're going to talk about two things here. We'll talk about the first one to be first principle of mathematical induction, which we normally are used to that. Okay, so I'll just take you guys through three examples of that, and after that, we'll do another video tackling what we call strong induction, and that is so cool. So the first principle of mathematical induction actually comes with this. First, you have some claims you're supposed to make. Two steps actually, I call them. The first step is called base case, right? So you'll be presented with a proposition saying that some proposition is actually true for some index n. Okay, so if I tell you that some defined function, maybe p of n, is true for maybe an n belonging to the natural numbers, then what you do is you show to me that indeed the base case when n is equal to 1 is true. So the base case is you show that p of 1 is true. When you show that, then the next thing to do here is going to be going to what we call the inductive step. Okay. With the inductive step, what is being entailed here is assuming that for some arbitrary n equals k, or you can say n, is true. So you assume that p of k is actually true. So for some given n equals k, then you show, you work out and show that p of k actually implies p of k plus 1. What this statement here means is that you're supposed to use p of k to prove that indeed p of k plus 1 also is satisfied. In other words, you're supposed to show that for n equals k plus 1, p of k plus 1 is true. Alright. So if you're able to do these two things and you show them, then you've proven your proposition. And using these two methods is what we call the first principle of mathematical induction. The next one I said is called strong induction, and then we'll do another video tackling how to solve that kind of problems. Okay. With that, the only difference is that mostly your base case are so many, they are more than one. That is what happens in strong induction. Now the first problem here is that I have a proposition here that we're supposed to verify whether this is true or false. Okay, for n equals n belonging to the natural numbers, so of course this guy is every natural number I pick, the sum of the first n odd numbers is equal to n squared. So in particular, I've defined the definition of your odd numbers here, and it's equal to n squared. Now notice that for an odd number, it can be defined whether you define it this way, 2n minus 1, or you define it 2n plus 1. In one of these defines an odd number, but here the indexing here is that n is starting from 1, and then here the indexing is that n is starting from 0 all the way to 1, 2, and the rest the same thing here. So notice that when n equals 1, the first one you get here is actually 1. When n equals 0, the first one you get here is 1. So both of them will generate all the odd numbers for you, but depending on your indexing. Okay. So what the first principle of mathematical induction says is that you're supposed to assume some p of n. So assume that this statement given here is your p of n. P of n is such that this guy here is actually equal to n squared. When you sum the first n odd numbers, you get n squared. So you pick when n equals 1. Right? We are starting from 1. What happens? P of, per the definition they gave here, that's why I started from 1, because per the definition, this is an odd number definition with indexing and starting from 1, right? So you do that. So P of 1 is such that now you pick the first term, 1, and what happens? This should be equal to 1 squared, so that it should be true. Now, what does this tell us? This tells us that indeed 1 is equal to 1 squared. And so P of 1 is actually true. So that's your base case. So ideally we're supposed to start with probably let me push it down, maybe, let me see, to do that I'm gonna push this whole guys down. So sorry, sorry for this, guys. I'm so sorry. Let me put it here. Yeah, still not selecting the proper one. Okay, yeah, I think I've got it. So let me put it here and then try to erase the top one. Okay, so we can erase this guy and then start with a proper definition. So what you're going to do is you start with the base case, right? So with your base case, this is true, right? So you just done with your base case. Then the next thing is your inductive step. Okay, inductive step. That step is telling us that we assume that, so suppose for n equals k, P of k is true, right? So that's what you do. This means, all right, so this means that, what does this? It means that if I have 1 plus 3 plus all the way to 2k minus 1 should give me a k squared. This step is very, very important. Okay, you're going to use it almost all the time. Now we're supposing that this guy is true, and then we've been able to write P of k in this manner, right? So what you're going to do is, what does this tell you? Now let's consider something. I just want us to work on the same screen, and because of that I'm going to clean this guy. Maybe that wasn't necessary. I don't know, maybe let me work here, if that will be fine. I'm going to work under this guy. I'm going to work here. Okay, let me order it. I just want to add a page. Okay, so this is what we have. We have that P of k is such that 1 plus 3 plus plus 2k minus 1 is equal to k squared. So that is our inductive step. Now let's consider this guy. Consider n equals k plus 1, right? What can you say about this left side here? When n equals k plus 1, it means you're going to have 1 plus 3 plus all the way to, you get to 2k, right? Then plus 2 into k plus 1 minus 1, right? That's what you get for the left side. Now what this is going to tell us is that we are supposed to be able to simplify this so that when n equals k plus 1 is giving us this, we're supposed to make sure that this whole guy will simplify to k plus 1 squared. That is the definition given, right? So that's what we're going to do. So for now, assume that you don't know this guy yet. You don't know that indeed it will give you k plus 1 squared. Okay, so this whole thing, let me rewrite it again, is the same as that. 1, 2, 3, 2k minus 1. If I simplify this guy, I'm going to get 2k plus 1, right? Now, what is this side of my k plus 1? That side is telling us that it's equal to what? K squared, right? So I just put it there. And that's going to be very fun. Okay? If you put it there, you have k squared plus 2k plus 1. Now, what is this expression? Notice that this whole expression here can be simplified as k plus 1 squared. So indeed, yes. Sometimes you're supposed to be able to build these guys, try to, learn how to, or you can review on how to do factorization of, quadratic functions or quadratic terms or expressions. I mean that's supposed to be the right word. Quadratic expressions or maybe quadratic functions. So if you do that, you're going to get this. Right. So it means for p of k plus 1, we have that p of k plus 1 is such that 1 plus 3 plus plus 2k minus 1 plus 2 into k plus 1 minus 1 is equal to k plus 1 squared. And so that is your proof. So you conclude that then the claim is true by mathematical induction. So then the claim is true by mathematical induction. All right, I'm going to call it MI. So yeah, that's how you use the first principle of mathematical induction to prove such issues. Now let me just quickly walk you through this and see if we still have, let's try and work this out. So I have a problem here that says that for all integers n in natural numbers. So this means we're talking about natural numbers. Recall that integers or natural numbers are still integers, but they are the positive side of the integers, right? We have that 5 divides n squared minus n, right? So what this 5 divides n squared minus n means is that when you have n being in the natural numbers, n squared minus n, oh sorry, I said n squared, n to the power 5 rather, n to the power 5 minus n can be rewritten as 5 times some expression. Or maybe after you simplify and divide by 5, you get some value, okay? Or you can say that, which is equivalent to saying that n to the 5 minus n over 5 is equal to some constant for all n in the natural numbers. All right, so first you go to your base case. What is the base case? We can start with n equals n starting from 1. Even if n start from 0, this is true. All right, this will be true. Notice that when n equals 0, you're going to have 0 to the 5th power minus 0, which is 0. Now if I divide this guy by 5, I'm getting 0. So here my a is going to be 0. So it's actually true, which is trivial, and I don't want us to work with that. Let's work with when n is equal to 1. Okay. Actually, you can pick n equals 0 as your base case. So for n equals 1, what happens? P of 1 is such that I'm supposed to show that 5 actually divides 1 minus 1. I mean 1 to the power 5 minus 1. And again, this is telling us that 5 divides 0. Right? 5 divides 0 means, 0 can be written as 5 times something. 5 times some constant. Where here, indeed, 0 is equal to 5 times 0. So here, a is actually equal to 0. So this is true for our base case. Now we go to our inductive stage or maybe case, which says that for n equals some arbitrary k. All right, let me use a different pen here so that we see what is happening. This guy is such that p of k means that what 5 divides k to the 5th power minus k. Okay, so that is true. We just assume that. Suppose this is true. Okay, so suppose this is true. Then what do we consider? We consider something here. Consider n equals k plus 1. When n is equal to k plus 1, what happens? Notice that before I start with this, we can try to look at something. But before anything, let's look at how this guy simplified should be. I think that's going to help us. We know that 5 divides k to the 5th power is the same as saying that k to the 5th power minus k is actually equal to 5 times some constant a. That is the definition of this guy. Now we can consider k plus 1, So we want to make sure that if you put k plus 1 in place of k here, we can write it as 5 multiplying something. Okay. So you take k plus 1, so we consider k plus 1. So you can actually be writing those English, or you can stop. Consider this. N equals k plus 1. We want to make sure that if we put k plus 1 here to the power 5 minus k, we want to make sure we can write this as k to the power k plus 5 times something, sorry. Now this guy, what is this expansion, right? So you can try to use your Pascal's triangle, where when your power here is actually 0. Okay, I'm going to do that here. When you don't have any power, let me remind you small. We're going to review that. When you have 0 power, your coefficient is 1. When you have 1 power, your coefficient is 1, 1. 2, you have 1, 3, 2, 1. When you have 3, you have 1, 3, 3, 1. 4, you're going to have 1, 4, 6, 4, 1, 5. I have a power of 5, so I'm going to have these coefficients: 1, 6, 10, 10. Did I say 6? This is going to be 5 rather. This is 5. That's 5, and I have 1. So what this guy that I've done at the top here means is that you pick the first one. I'm going to expand this guy. You pick this guy. You're going to get k to the power 5. That's the coefficient of that is 1. And plus 5. That's the coefficient there. They multiply by k to the power reduced by 4 by 1, and you have 4. And then if this guy was not 1, then you pick it and raise to the power 1. But if I pick 1 and raise to the power 1, I still have 1. So I'm going to continue with that. And I'm going to have that the next coefficient is 10 k cubed, 10 k squared, 5k, and plus 1. Actually we left something. This is plus 1 here. We're considering n equals k, minus k plus 1, right? Now if you look at it clearly, you get k to the 5th plus 5 to the power that plus 10 to the power 3 plus what is it here? I have 10 to the power k squared plus 5k. Where do I get again? I have plus 1 minus k minus 1. So this guy minus k plus 1 can minus 1 plus 1 can go, but notice something: do not subtract this guy from this 5k, because it's going to help us. If we subtract, we're going to have an issue. Now this means I have my k plus 1 to the 5th power minus k plus 1 to be k to the power 5. I'm going to let you know what I'm going to write. K to the power 5 here minus k. I'm going to put it down, minus k. Then I'm going to write the rest of these guys, 5k to the 4th plus 10k to the 3, 10k squared. I guess we have plus 5k. That is the last one. Now what is this guy? This guy here was 1k. We assume that when n equals k is true, so that's that guy. So k to the power 5 minus k has been assumed that it can be written as 5 multiplying some constant. Alright, so you're going to have 5a here plus 5k to the fourth plus 10k cubed k squared plus 5k. The whole of this is going to give you 5 into a plus k to the fourth power plus 10. I'm sorry, that's going to be 2k cubed plus 2k squared plus k. Now, the most important thing is, what is this whole thing? Notice that k is an integer, a positive integer. So if k was a number and I put it here, when you simplify this, what will you get? You're going to get a particular value. Let's say p. It's also going to be a number, right? You're going to get some number. So this whole thing is going to be giving us 5 multiplying p, where p is given by this side, right? So k plus 1 to the fifth power minus k plus 1 has been able to be written into 5p. Again, where our main focus was supposed to simplify k plus 1 to the 5, minus k plus 1, to be able to be written as 5 multiplying some constant or some integer or some number, right? And so since this is true, this implies what? It implies that 5 actually divides k plus 1, 5 minus k plus 1. And this is true. That's what we wanted to show, right? We wanted to use the p of k. Notice that we use the p of k at this point, right? We use that to show that p of k plus 1 is true. So here the claim is also true. Claim is true by mathematical induction. And that's it, right? So the first principle is just telling you that you start with some base case, one of them, and you assume, your inductive step, that p of k is true. When p of k is true, you go ahead and use that to also show that p of k plus 1 will give you the expression that was given in the problem. Here, the expression that was given here was 5 will always divide, n to the fifth minus n for whatever natural number you pick. Now here we went all the way up to k plus 1, and indeed 5 is dividing that guy. This is cool, right? So you can actually do this, this very, very far. I think it's going to be very, very long, but I'm hoping that you'll be able to solve this guy. First you assume that your n equals 1, and for n equals 1, p of 1 will be such that this guy, 1 multiplying 2, which is 2, should be equal to, when you put 1 inside the whole of that, you have 1 plus 1 plus 2 over 3, and indeed this guy is going to give you, here will give you 2, this will give you 3, and that 3 can take that guy out, so you're going to get 1 times 2. So p of 1 is true, right? Then you assume that p of k is true. That is your inductive step, so that 1 multiplying 2 plus 2 multiplying 3 plus all the way plus k multiplying k plus 1. Notice that this expression is as a result of this k. Is equal to k into k plus 1, k plus 2 over 3, right? Then you consider when you add a k plus 1 to this side, what happens? Make sure you simplify that guy to make it look like something like this in terms of k plus 1, right? So for p of k plus 1, what's going to happen is you have 1 multiplying 2 plus 2 multiplying 3 plus all the way to, before you get to k plus 1, you're going to have this guy. Then with k plus 1, you're going to have k plus 1 into k plus 1 plus 1. So you can leave it like this, right? But this guy has been given, this side has been given as this. So you come and put it there. K into k plus 1, k plus 2 over 3 plus k plus 1 here, this guy here, k plus, you can make it 2, right? That is k plus 2. Then how do you simplify this? This is a quick fraction, right? I want to do this very quick. I wanted you guys to try it, but I think I just kind of can't stop myself from solving this problem, right? So let's solve it together. You multiply 3 to this side, to this guy here. And when you do that, or you can try to rewrite this as divided by 3 multiplying 3, and it's the same thing, right? So when you do that, you have k plus 1 here, k plus 1 here, k plus 2, k plus 2. I can add, but I can actually add them. So let me add them first. K into k plus 1, k plus 2, 3 or plus 3 into k plus 1. I mean, this 3 here, just push it front there. K plus 2, all of these over 3. Notice that if I divide each term by 3, I mean this whole side by 3 and this whole side by 3, I'll get back my original fraction. Okay. Now I have some terms happening in both sides. I have this whole thing here and I have it here as well. So I can factor it out, right? So I can do this as k plus 1 into k plus 2 into what? K plus 3, right? Because when I factor this side out and this guy out, here we'll be left with 3, and that is this 3. Here we'll be left with k, and that is this k, right? So actually we've done nothing new. All of these over 3. Now what does this tell me? Like it's telling us that this whole thing here, notice the definition. The definition is whatever n you pick is going to be n into n plus 1 into n plus 2, right? Here we picked n to be equal to what? N was k plus 1. Can we simplify this into, the first term is already k plus 1, so I'm having my k plus 1. The next thing is supposed to be the n that you pick plus 1, right? This time, notice that this is our n, so just put it there. Now I'm going to have n plus 1. It means it's going to be this guy. But I don't want to write it as k plus 2. I'm going to have k plus 1, which is my new n plus 1. And I hope that makes sense, right? This is going to be, the next thing is going to be your n plus 2. So it's n into n plus 1 into n plus 2. Now, instead of me to write k plus 3, I'm going to call it k plus 1 plus 2. Notice that our new n again is k plus 1 all over 3. So when n equals k plus 1, we've been able to prove that yes, the expression at the left can be rewritten as k plus 1 multiplying k plus 1 plus 1 multiplying k plus 1 plus 2 all over 3. And so this has been able to be simplified into the expression that we want, right? So this is true. So the claim is true for all n, by the mathematical induction, right? So basically, yeah, that is it. That is how you solve or you try to prove propositions when you want to use mathematical induction. Okay, I mean, this is the first principle of mathematical induction, and I just took my time to walk you through everything. You can actually learn it and equip yourself with that. In our next discussion, you're going to talk about what we mean the strong induction. All right, thank you, and don't forget to subscribe to my channel if you have not subscribed. Like my video and also comment what you think about this video on the comment section. Okay, see you.